Hello students. In this lesson today we're focusing on areas under curve, and that is that we're looking at areas between the curve and an axis. Most of the time this will be areas between a curve and the x-axis, so that means we're looking at the integral of f of x with respect to x as the area, but sometimes it can potentially be the area between a curve and the y-axis. And so that means we're looking at the area as an integral of a function of y with respect to y. So the areas under the curve, we'll be looking at focusing on that fundamental theorem of calculus that was covered in the method syllabus, and that is when we're looking at some function f of x and we're trying to find the area under the curve between a and b. And that can be done by looking at the integral of f of x dx between b and a, and it will be the difference in the primitive when we substitute in b, or the primitive at point b and the primitive at point a. So in terminology, this f of b, that's a primitive, and essentially we're looking at the antiderivative or the integral between those 2 points. Okay, so it's a fundamental theorem of calculus. We'll be using that as our process for calculating the area under the curve, and our major focus is going to be on physical area, and that means we have to be careful with signed area. So for any function that crosses through the axis, if it exists above the x-axis, then we're going to have a positive area, and if it sits below the axis, this is x and this is y, so it's only the axis that we're talking about, this will be a negative area. So we need to be able to deal with that. When we're looking at area, we're considering physical area, and so therefore, depending on whether it's above or below the axis, it will give us a positive or a negative area. Now we don't want to consider negative area, so we have to be able to deal with that using an integral approach. So if we look at this as points A, B, and C, if I'm looking at the physical area, there's a couple of ways I can do that. So first of all, we should probably note that the area between C and B of our function will be a negative area. To make that positive, we can look at flipping the limits, so making it BC f of x with respect to x. We can subtract it, so instead of adding it, we can say this is negative CB f of x with respect to x, or we can look at using the absolute value. I'm not going to stipulate which approach you take as long as you apply it in the right way. So if I was looking at the area here, I would simply say the area is equal to the integral between b and a of our function, subtract the integral between c and b of that function. Or I could say that the area is between b and a of the function plus the absolute value between c and b of the function. Of course, I could also say that the area is equal to the integral between b and a and the integral between b and c, so flip those limits. So these three expressions mean the same thing, and it will allow us to calculate the physical area rather than having a positive and negative area working against each other. Alright, so these should all be concepts you covered in mathematical methods. What we're going to do now is we'll look at a couple of examples, and the lesson will be a review. Okay, so for our first example, we're looking to determine the area of the region bounded by the curve x squared take 4x plus 3 and the x-axis. So the first thing we need to be able to do is draw a relative sketch of this function. So I will pull up my graphics calculator so we can do that. So if we start by sketching this function, we can either do this by hand or using our graphics calculator depending on the scenario. I'm going to put this into my graphics calculator. So x squared, take 4x plus 3. We draw this and we've got a good indication of what we're looking at. It says determine the area of the region bounded by the curve and the x-axis. So we're looking at this area between the x-axis and the curve. So we have to start by looking at the x-intercepts. So the x-intercepts will occur at, now we go g-solve root. We've got x equals 1 and we have x equals 3. So these determine our bounds. What we're really looking at then is the integral between 3 and 1 of our function x squared take 4x plus 3 with respect to x, and that's going to be our physical area bounded by the curve. Now, if we want to use our calculator at the start to determine what the solution should be, we can hit G-solve, we can go across, we can look at the integral, which is f3, and integral f1, we're going between 1 and 3. So we can see there's negative 1.33 reoccurring, or we should know straight away that our answer should be the area is equal to negative 4/3 units squared. Okay, so let's go through our process. This will be x cubed on 3 minus 4x squared on 2 plus 3x between 3 and 1. So that is, we've got 1/3 x cubed take 2x squared plus 3x between 3 and 1. So 1/3 multiplied by 3 cubed, take away 2 times 3 squared plus 3 times 3. Subtract 1/3 by 1 cubed, take 2 lots of 1 squared plus 3 lots of 1. So this is 1/3 of 27, which is 9. And we're subtracting 2 times 9, which is 18. And then we're adding 9. So this should end up being 0 in this bracket. And here we have 1/3 subtract 2 plus 3. So we have 0, subtract 1 and 1/3. And so our final answer is 4/3 or 1 and 1/3, which is what we would have expected to be based on our calculation at the start. Alright, second example, we're looking at determining the area between the graph of y is equal to x over x squared take 1, the x-axis, x equals 2, and x equals 3. So we'll go back and we'll put it in again so we have an indication of what we're actually finding. We've got x over x squared take 1. And we're focused only between 2 and 3. So G-solve integral between 2 and 3. Okay, so we have this small area over here. So if we draw a quick sketch, looking between 2 and 3, and so this is the area that we're focused on, and that area should be approximately 0.49 units squared. Alright, so for us, I'm going to first consider the integral of x over x squared take 1. Now we can treat this as a special quotient rule, or we could do a substitution. I'm going to go special quotient and say that I'm looking at this as 1/2 of 2x over x squared take 1. As the numerator is the derivative of the denominator, this is 1/2 ln x squared take 1. So when I'm looking at the integral of x over x squared take 1 with respect to x between 3 and 2 as my area, it will be 1/2 ln x squared take 1 between 3 and 2. And so we have 1/2 ln of 3 squared take 1, subtract 1/2 ln 2 squared take 1. So we have 1/2 ln 9 take 1, which is 8. Subtract 1/2 ln 4 take 1, which is 3. And when we bring that back together, we've got 1/2 ln 8 on 3. And units squared. Alright, so hopefully that makes sense. We use that logarithm rule to simplify it in the end, but that gives us an indication of our area under the curve between 2 and 3. When we look at the third example, this one's a little bit more complex. So if we go back out and we start by sketching it, we've got x cubed take 9x. We can see that there's an area above and below the axis. So when I sketch this one out as a rough sketch, I've got two areas that are bound by the axis. So that means I've got area 1 and area 2. Now obviously area 1 will be a positive, area 2 will be a negative. We need these intercepts here. These intercepts will be important. So gsolve, and we'll find the roots. So we have -3, we have 0, and we have 3. Of course we could go through the process of solving this by hand as well, but that's not the focus today. So now we've got that the area, that physical area, is the sum of the area between -3 and 0 of x cubed take 9x with respect to x. And then we're subtracting. So because we know it's going to be negative, if we take it away it will become positive. Subtracting between 3 and 0 x cubed take 9x with respect to x. So this becomes x to the power of 4 on 4, take 9x squared on 2, between 0 and -3, and we're going to subtract x to the power of 4 on 4, subtract 9x squared on 2, between 3 and 0. So we have, in the first one, 0 subtract -3 to the power of 4 on 4, take 9 -3 squared on 2, and we're subtracting 3 to the power of 4 on 4, subtract 9 times 3 to the power of 2 on 2, take 0. So we have -81 on 4, take away 81 on 2, and we're subtracting 81 on 4, subtract 81 on 2. So we have -81 on 4, take away -81 on 4, which leaves us with 81 on 4 plus 81 on 4, which is 81 on 2 units squared as our final answer. Now, really it ends up being 2 times this area, so if we go gsolve, find the integral between 0 and 3, end up with -20.25, which is 81 on 4. Obviously, that represents the second bracket, and when we have two of those put together, we end up with our 81 on 2. Okay, so our last example, we're looking at calculating the physical area between, again, the curve and the lines y equals 0, x equals 1, and x equals 4. So now we're defining it between 1 and 4. So we want to take the same approach. We will graph this, x plus 2, x take 3, and 2x take 1. And we can see that it's, again, a similar polynomial. But because we're only looking between 1 and 4, then if we go gsolve and we find the area between the curve, and we're looking between 1 and 4, we can see that there's a negative section and a positive section, so we need to be able to break that up. Obviously, there's an intersect at x equals 3, so what we're saying is that our area is the integral. Now it's negative between 1 and 3. So if we go 3 and 1 and we make this absolute value of our function, with respect to x, and then we can add in the integral between 4 and 3. Okay, so to do this one by hand, we'd have to expand out and simplify. I'm going to do this on my calculator just to show you how to do that. So we're going to say math integral, and our function is in 1. So if we go vars, we're looking at graph, and we want y1. So if this is between 3 and 1 and we want to make it positive, we'll just go absolute value, or it's probably easier just to put the negative in front, plus, and again we can go math integral and vars graph y1, and this time it's between 4 and 3. We can calculate that and we get our area of 36 units squared. Alright, so just a note, if we were doing this by hand before we integrated, we'd want to expand this out. So you'd want to be able to say that y is equal to x plus 2x take 3, 2x take 1. We'd expand the first two brackets and we'd have our x squared take 3x plus 2x take 6 multiplied by 2x take 1, which would be x squared take x take 6 multiplied by 2x take 1. And multiplying by 2x first will give us 2x cubed take 2x squared take 12x. Multiplying by negative 1 give us take x squared plus x plus 6, and that all works out to be 2x cubed take 3x squared take 11x plus 6. And so we'd be finding the integral of this function between 3 and 1 and 4 and 3 and looking at the sum of those. If we flip back to the graph, we could also do it in those two parts. If we find first gsolve integral between 1 and 3, we can see that that's equal to negative 18. And then if we find gsolve the integral between 3 and 4, that's positive 18, so 18 plus 18 gives us our 36 units squared. Okay, so that concludes the lesson. It's a lot to review. It's pretty much all our basic understandings from methods. Make sure that you're comfortable with these processes, and in particular you're comfortable with breaking up into those physical areas, positive and negative, and addressing the sign of those particular sections. Okay, thank you for listening.